Thank you for joining us today. I'm Phani. I'm an engineering manager at DoorDash. I'm part of data platform organization. I lead data infrastructure, quality, and governance teams. This is Ivan, our tech lead on data infrastructure team, primarily focused on two key elements, data orchestration and data ingestion. Today, we want to share how we solved near real-time data ingestion at DoorDash scale using Spark and Delta Lake. To set the context, many years ago, during the early times of DoorDash, the main business problem we are trying to help solve is around a set of analytics questions rooted in historical context, such as how many orders did we do yesterday, how many deliveries did we deliver last week. During the early days, largely DoorDash service is a monolith with a large backend database. So the simple approach to answer a lot of these analytics queries is to create a dedicated reader/analytics replicas and direct all the analytics queries to that. Over the period, as DoorDash started evolving with the business demands, quickly the monolith has been re-architected into multiple microservices with many databases for example, order, menu, so on. That demanded the need to have an ingestion framework to bring the data from online databases into analytics ecosystem modeled for OLAP purposes. So when we started looking into building an ingestion framework, the ask is, what is the outcome we are going to solve for? It's not just purely for a set of predetermined analytics queries, but actually we want to get the data from databases as in the simplest way so that we can answer a lot of open-ended questions. The simplest approach, again, we took in very early days, probably 6-7 years back when we started building this, is just doing a snapshot of each of the table that we want to ingest and replace that snapshot every day with the target analytics table. As you can imagine, this has obviously velocity constraints. We can only do at most once a time. For certain tables over a size, it's sometimes once a week. So you are looking at latencies anywhere over 24 hours. DoorDash started growing, especially with the international expansion and growing into the newer verticals, which demanded having data at much faster frequency. That led to us, again, looking at the simplest way, the quickest way to get the data. And we arrived at a very point-based solution, essentially determining the set of tables that needs to have this faster ingestion, working in collaboration with the data engineering and analytics teams, going back to product engineering teams, establishing a very loose contract of having a time-based column, which we heavily depended on to determine the delta and merge that into the analytics ecosystem. As you can imagine, with any intraday ingestion, the biggest challenge we got to tackle is around schema management. The naive approach we took is around scanning the metadata of these online tables, determining if there's a change, and if the change is backward compatible, reconcile the schema, go along and merge. If the change is backward incompatible, that introduced friction with human involvement, on-call page, further coordination with the downstream dependencies. Sometimes to rebuild and restore, especially with the large tables, it took multiple days. Now, think about doing this at scale. If we have to take this point-based solution and make it more of a generic and guarantee every data set to be available under certain latency, it's just not possible. One, humanly impossible with the on-call burden to handle those incompatible changes. Two, operationally not sustainable with high risk of data loss as well as data being unavailable for multiple days. Along the lines, adding to the complexity, we also had to deal with migrating from one cloud data warehouse to another cloud data warehouse for various scaling challenges. That's a whole another topic to discuss. I will not delve into it. That also forced us to invest in building an orchestration system which guarantees intra-DAG dependencies. At the end of 2020, we have about 1,000 plus data pipelines ingesting data from online databases into analytics ecosystem. Majority, about 90% of them, continue to rely on daily refreshes. About 10% were depending on the incremental refreshes, again, based on a time-based column that need an index on that for it to be performant enough for us to ingest every few hours, and a very loose contract with the product engineering teams who owns those microservices to respect that contract of updating the time-based column with every write operation. which is very loosely held, sometimes leading to data losses. We also had introduced cockroach database in DoorDash during that year, which has certain out-of-the-box CDC features, so we started exploring them, but continued to rely on old design principles of having a time-based column. I know I talked about a lot of challenges, a lot of operational issues. To answer these, we embarked on a project called Pepto. As you could see the tagline, it is to solve for the indigestion of our data processing frameworks. The requirements for Pepto are pretty clear. First and foremost, guarantee the P99 data latency under 15 minutes. Build an open source based ingestion framework that is future-proof, extensible, and doesn't get us into any vendor lock-in. The design tenets we leaned on pretty heavily at the initial stage is zeroing on Kafka as our central nervous system, where all the change feeds get published to and consumed from. This allows the extensibility I was talking about. Then, write once, read many is another key design tenet. We will talk about that, how it helped certain design choices we made further in the talk. Operational simplicity is a big requirement, given the operational burden we are facing with our existing frameworks. Dev velocity in terms of onboarding times are very key considerations when we started building out Pepto. What Project Pepto is not, it's not a coupled service with any database. Meaning, if you introduce a new database into DoorDash ecosystem tomorrow, we will not be in a state to re-engineer the whole ingestion framework, whereas we'll only be needing to allocate few engineering cycles to write a consumer adapter to consume the change feeds from this new database. It's also not a real-time system. Some of you may be aware, DoorDash is a very prominent adopter of Flink. Our colleague, Allison, is actually giving a talk tomorrow on Flink Delta Connector. I highly encourage to attend that. The clear demarcation for us is a Spark-based framework like Pepto is meant for data movement between online databases and data lake, guaranteeing the freshness in magnitude of minutes, whereas Flink-based real-time processing framework is meant for consuming online events that gets emitted from our microservices, guaranteeing freshness in magnitude of seconds. With that, I will hand it over to Ivan to dive into the technical details of Pepto.
Thanks, Phani. So I'll start off the talk with a quick system architecture diagram. Up top, we have our sources of all the database flavors that we support in DoorDash, PostgreSQL, Cassandra, and CockroachDB. They emit CDC records or change data capture to Kafka. We don't really care so much about what the format of these records are, nor do we really care about the operation. We just care that they are emitted to Kafka, which is our boundary for a lot of the communication between and the contract set between us and the core infrastructure and storage teams that maintain those stateful stores. Then following afterwards, that's where we sort of get involved on the consumer side. We have a Spark stream that reads from the protobuf, a schema registry that we have that understands what the schema of the table is going to be, applies that schematization to the Kafka topic, and then does a merge and upsert to Delta Lake S3. I think there's been a couple talks in the last few days about having a unified source of truth in Delta Lake. That's what we try to achieve here. We also expose that to various near real-time query interfaces within our ecosystem, dashboarding tools like Mode and Superset, Trino, and Databricks SQL. For backwards compatibility purposes, we also have a daily egress up to Snowflake just to snapshot and have that for backwards compatibility purposes. I also haven't really talked about this, the sort of the snapshot mechanism on the far right. That's just on rebuild or when we ever need to do an initial snapshot, where this is getting an entire view of the database, and we don't do it through Kafka. I think there's a concept in the data processing world called like Kappa architecture. For those of you who are familiar, it's you send the entire snapshot through the stream itself. And we've elected explicitly to not do that. I call it not Kappa architecture because there's not a really good name for it, but the design decision here is that even though, if on a snapshot, you can imagine jamming a 16-lane highway down into a residential neighborhood lane. And while you can solve auto-scaling on the consumer side for something like Kafka topics and partitioning, auto-scaling on the producer side is very difficult. And that can have SLA contract breaks in terms of data delays. And so we opted to increase operational complexity of our system to prevent these kind of data delays. Another main design decision that we had was freezing schemas in the schema registry. I think we mentioned before that we would get paged on a backwards incompatible schema change, and that operational burden was very tough to maintain. And so we introduced the schema registry to sort of freeze it and ensure that we could control the compatibility of the schema as it changed. So unfortunately, what the product engineer had to do was, if they changed it on the database side, they also had to change it in the schema registry to ensure that the column was reflected. And then finally, I think this is sort of a hot topic in the industry about Delta Lake over other table formats. We wanted to do a table format because we wanted the ACID compliance or transaction guarantees that came with that file system. The three main file systems, table format, sorry, Apache Hoodie at the time of this decision, while it has a CDC Delta streamer and indexed, and probably would have been very performant for this. If you are curious, the Robinhood has a great blog about this. At the time of this decision, Hoodie did not have a connection with Snowflake, which was table stakes for us because we were a heavy Snowflake user. Furthermore, at the time of decision, Apache Iceberg was only supported merge on read, and we explicitly made the decision to to do copy on write. Our title is a mouthful because we want it to be explicitly near real time. We operate on the order of minutes, not seconds, and that is the problem we are trying to solve in terms of upserts here. So I'm going to go a little more into detail about that consumer side. When you introduce a snapshot or a rebuild, you have to manage a lot more states. So we have three states. The first state is the steady state mode. It's probably what happens 90% of the time. We'll have Airflow orchestrate and just basically essentially emit an API call to the Databricks API call to check if the stream's running. But what the stream does is it reads the records from Kafka, reads what the schema is in the schema registry, applies the transformation, and then does a merge on the last known state. So essentially an upsert. It'll write to two destinations, what we call like the snapshot table on the right bottom over there, and the audit table. And you can imagine the audit table as just like a list of every single write operation for every single primary key. Essentially a transformation of the Kafka topic CDC records coming in, deduplicated. Now, when we start triggering a snapshot, that's where things get interesting. We start off with Airflow triggering a SQL command or to the source database to tell them, hey, please dump a snapshot to S3. In the same time, we'll trigger the Spark stream, orchestrate it to say, run in rebuild mode now. Rebuild mode has various similarities to the steady state mode. It'll still read from Kafka, still read from the schema registry, it'll still write to the snapshot and audit table, but it also writes to this new buffer table now. And the buffer table exists here to essentially do a little bit of time checkpointing to ensure that when the snapshot is written, there's no data gaps between when that snapshot started and when the stream started. So moving on. When that snapshot is complete, basically what we'll do is subsequently do a batch merge mode. And that will take the snapshot, the buffer, merge them together, and then overwrite to the table. This is sort of a force overwrite. This is sort of our saving grace to blow away any sort of backwards incompatibility schema changes and ensure that we can sort of have compatibility moving forward. So yeah, I think overall, I wouldn't say this is conceptually a very, very difficult project in and of itself. I think the challenge comes in productionizing it and removing, trying to democratize a lot of the onboarding experience. And so historically, when we wanted to sync a table, it would take over 24 hours and require intervention with both the core infrastructure teams and the data infrastructure team. So we've essentially moved both of ourselves out of the equation and have an onboarding down to less than 1 hour. Most of the time is actually just waiting for PRs to merge more than anything. We have about 450 streams. One Kafka topic maps to one Spark stream, which maps to one database table. We have about over 1,000 EC2 nodes running in production 24/7. We ingest from Kafka about 800 gigabytes of data, and because of this copy on write concept, we rewrite about 80 terabytes of data per day. And we have a data latency, because this is in a streaming manner, we have a latency of about 7 to 30 minutes. We actually micro-batch it, so we don't actually have it in permanent streaming mode. To make things the upstart more efficient, we actually set a window of a trigger of every 5 minutes to ensure that is more efficient. Here's just a quick graph of what we see from the observability side. Basically, you can kind of see like the number of rows ingested, updated, or updated and inserted, sorry, and then sort of the main step of operations, in terms of how long it takes to deduplicate the records and how long the merge operation takes. And then sort of up top here, you can kind of see the perceived latency of the table. So I think this is a 2-year endeavor in terms of the project timeline. A bunch of learnings from this. First off, I think checkpointing solves a lot of problems. Spark streaming or streaming in general is operationally tough to sort of get started. But once you get a stream, once you solve those problems or get that musculature from an engineering perspective, it actually solves a lot of your problems. There's a whole concept of going from streaming workloads to batch workloads, and if you've ever had to do with partitioning by hour, you've had to deal with late arriving data, how to dedupe over certain partitions, watermarking, et cetera, et cetera. Streaming solves that problem by removing the problem altogether. If you think of everything as a stream and set contracts to say, hey, my data is good, the table is going to have an SLA of 30 minutes, and if you want to have the latest data for the last hour, just run at 30 minutes past the hour, and your problem is essentially solved. You don't need to do all of these late arriving data to ensure reruns or et cetera, et cetera. Second, type conversions are hard. I think it's explicit. I want to call out explicitly, because we didn't do this whole Kappa architecture of fitting everything through a stream, and we had 2 methods to get the same data to one source, we have to have 2 different serializers for every single adapter. So for CockroachDB, our main supporter, we have to have 2 ways to serialize and parse decimal types, geography types, timestamps, binary blobs. Like that makes conversions a lot harder to catch edge cases, and has shown to be challenging in the past. Another thing to mention is that large tables are operationally challenging. This is a copy and write, so you do need a lot more compute power to be able to do what you want. But our goal for this project was to wrap a lot of the configuration away and sort of abstract a lot of the Spark configs away from the production or microservices engineer. However, for large tables, concepts like Spark's, the number of shuffle partitions, what node types, how many nodes you want to have it, and other various Spark configs, we couldn't exactly abstract away. We couldn't use a lot of those features. So intervention from at least the data infrastructure side was needed to help set those tables up correctly, such that you could have fulfill those latency requirements. Finally, actually no, not finally. State management. I think in the three diagrams I had described before about steady state, rebuild, and batch merge, I only really talked about the happy path. Once you start incorporating failure modes, what happens if the API fails, call fails? What happens if an EC2 node goes down on the Spark cluster? What happens if Airflow doesn't respond or takes the container is rotated? All of these state management failure cases explode our state machine, and there are a lot of edge cases to track. One simple thing is just make everything idempotent. Idempotency is sort of, if you think about it to implement how to, idempotency ensures that you can run the same job the same every single time, and that solves and reduces a lot of complexity in any system, really. And finally, just want to sort of shout out on reputation. I think this project wrote these tables in parallel to the legacy database syncs that were going on. And so naturally, there is a bit of a migration. You have to, and in this migration, you have a cutover. And so from this, you have, as you're cutting over, as people are looking at the data, it's very hard for them to sort of believe that this is correct. And the second they identify an issue, they'll come out with the pitchforks. And so the moral of the story here is to just have data quality as a first-class citizen. I think there's a lot of talks going around here that also talk about data quality. Would strongly recommend. I'm going to talk a little bit about our future work now. I think as we've stabilized operationally, it would be just sort of looking ahead on what's next for Project Pepto. Phani briefly mentioned about using those online databases to run ad hoc queries. That's CPU steal from the online database services. Database services should be indexed fast lookups reserved for the microservices. If you were trying to run a dashboard on a live database or even a replica, you're stealing it, the CPU that potentially can take a database down or at least have degraded services. We're seeking to open this up, this Delta Lake workload up to a lot of near real-time dashboarding now. So instead of plugging into the online microservice database through Mode or something like that, you would now plug into a lot of these Delta Lake tables, run your dashboards on top of it, and that would be non-blocking to the online databases, allowing for more stability. If you need to tolerate I think more time than I say 15 minutes, then you may need to go to the databases. But at least in terms of near real time solves a problem in that space where there are very few use cases in which a dashboard needs absolutely real time data. Second is PI obfuscation. Right now we just basically nullify everything. There's no granularity in how you do lookups, group bys, by various email addresses, device IDs, et cetera, so we want to introduce some sort of degree of granularity and some sort of PII governance and obfuscation to this structure. So we're adopting this sort of medallion architecture, this bronze, silver, gold concept. And we're going to be using streaming a second Spark stream that reads off of the current tables that we write to, and do streaming PI obfuscation based off of the Delta CDF or change data feed, I think. Yes. Finally, schema changes to the source. We have historically, like I mentioned before, we have a schema registry that we use to freeze the schema. It's annoying for a product engineer to have to change it in two places. It would be very nice if you could, go to if you make a schema change on the source database side, that just eventually flows all the way through. We have gotten to an operational point where we can begin considering handling that and accounting for backwards incompatible changes, and that's sort of on the roadmap.